Hi, my name is Caden Smith, and this is my fifth and final lab for Physics 2212. The purpose of this lab is to model a tube magnet system that exhibits Faraday's law in both an experimental and computational setting. Collect and compare data from both. The PDF states in this lab you will collect observational data of a magnet falling through a conductive tube of aluminum foil, as modeled on the right, model the magnet-tube interaction computationally, and compare your computational predictions with your observed data. This lab will explore a well-known phenomenon observed when a powerful magnet is dropped straight down a conductive, non-ferrous tube and falls out the other end. Fundamental principles, all of which are shown to the right, include Ohm's law, Biot-Savart law, Faraday's law, magnetic flux, and Newton's second and third laws. In this lab, both of the fall times were very similar, with around a 10 to 12% difference in the fall times. In this lab, the system is the bar magnet in the aluminum tube, while the surroundings is everything else in the universe. In this lab, we assume that the bar magnet acts as a magnetic dipole. The system is isolated in that there's no other magnetic fields that could interfere with the experiment. The magnetometer app operates correctly and gives accurate measurements, and air resistance on the magnet is negligible while within the tube. First thing we did in this lab is do the experimental model. The initial conditions were that the tube exhibited the following measurements, with the length being around 30 centimeters, the width being about 5 millimeters, and the inner radius and outer radius being about that same 5 millimeters, different at 1.5 centimeters and 2 centimeters. The magnet had a mass of about 0.025 kilograms, and its magnetic dipole moment was measured to be around 2.075. This resulted in an average time of falling across 5 trials of around 1.51 seconds. These times were measured using a stopwatch and the video of each fall. After completing the experimental model, I moved on to doing the computational model. This part of the code defines the constants and initial conditions of the computational model. These initial conditions are identical to those used in the experimental model. This section of the code is pulled from Lab 3, in which we calculate the strength of the magnetic force. This final section of the code combines the forces calculated for magnetic and gravity in order to model the motion of the magnet through the tube. This slide shows the computational data gathered through our lab, in which it took around 1.316 seconds for the magnet to fall out of the tube. The differences in our experimental and computational models suggest small errors occurred in the production of this lab. These errors may include timing inaccuracy, magnet strength inaccuracy, and bad readings via the magnetometer at the beginning of the lab. The intensity of the coloring of the tube indicates the magnitude of current flowing through each ring. Via Lenz's law, we were able to figure out that red represents counterclockwise while blue is clockwise current. When you flip the magnet around, the direction of the current flips, but the timing of the fall remains identical. Our real-world system gave a slightly higher amount of time than our computational model. This is because we did not use an infinite number of rings in our computational model. The shape of the velocity versus time plot is relatively flat while the magnet is inside the tube. This tells me that the magnetic force and gravitational force on the magnet cancel out at this time. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Because this is inversely proportional per Ohm's law to current, then our current would be extremely high. This would cause increased resistance, and the magnet would fall extremely slowly within the tube as a result. If it actually reached zero, the magnet would stop while within the tube. If holes or slots are cut into the tube, then the current rings would be lessened, and therefore magnetic force would decrease in magnitude, allowing the magnet to fall at a faster pace. This concludes my Lab 5 for Physics 2212.